Pick up any book on cosmology and you will find a diagram, a cone or a funnel expanding from a single point labeled the Big Bang, time zero, the beginning of everything. The image is so ubiquitous, so deeply embedded in popular imagination, that it feels like established fact. But here is the truth that Richard Feynman understood, and that modern physics is grappling with in profound ways. The Big Bang was not the beginning. It may not even be a bang. It is a phase, a transition, a moment of extreme density and heat that our equations can describe, but beyond which they falter and fall silent. What came before, if before even has meaning in that context, remains one of the most tantalizing and humbling mysteries in all of science. And the deeper you look, the more you realize that the story of the universe's origin is far stranger and more open-ended than the tidy narrative we were taught. Let's start with what we actually know. In the early 20th century, astronomers made a startling discovery. When they examined the light from distant galaxies, they found it was shifted toward the red end of the spectrum. This redshift is the hallmark of objects moving away from us. The farther the galaxy, the greater the redshift, and therefore the faster it is receding. Edwin Hubble plotted this relationship and found a simple law. Distance is proportional to velocity. The universe is expanding, not exploding outward into pre-existing space like shrapnel from a bomb, but expanding in the sense that space itself is stretching. Every point is moving away from every other point. There is no center, no edge, just a uniform, relentless growth of the cosmic fabric. Now run that film backward. If galaxies are moving apart today, they must have been closer together yesterday. Go back far enough and you reach a state where all matter and energy in the observable universe was compressed into an unimaginably small, hot and dense region. This is the hot Big Bang, a state that existed roughly 13.8 billion years ago. Notice the phrasing carefully. A state, not the origin. The distinction is crucial. The evidence for this hot, dense past is overwhelming. The cosmic microwave background radiation discovered in 1965 is the cooled remnant of that primordial fireball. It is a faint glow of microwave radiation coming uniformly from every direction in the sky, the afterglow of a time when the universe was so hot that atoms could not yet form, and photons scattered constantly off free electrons. As the universe expanded and cooled, atoms formed, photons decoupled, and that light has been traveling ever since, stretched by expansion into the microwave range. We are bathed in the light of the early universe, and its exquisite uniformity and tiny fluctuations match the predictions of Big Bang cosmology with stunning precision. We also see the correct abundances of the lightest elements, hydrogen, helium, and lithium, forged in the first few minutes when the universe was a nuclear furnace. Every test we can devise confirms that the universe was once in this hot, dense state. But here is the rub. When we try to push our equations all the way back to time zero, to the singularity, they break down. General relativity, Einstein's theory of gravity that describes the large-scale structure of spacetime, predicts that as you go back, density and temperature rise without limit. At the initial point, they become infinite. This is a singularity, a place where the mathematics screams that something is wrong. Physicists do not take singularities literally. A singularity is not a feature of nature. It is a red flag. It signals that the theory has reached the edge of its domain of validity. General relativity is a classical theory. It does not account for quantum mechanics, the physics of the very small. At extremely high densities and tiny scales, quantum effects become dominant. Near the singularity, spacetime itself must be subject to quantum uncertainty. Distances and times lose their classical meaning. The smooth fabric of spacetime predicted by relativity gives way to a roiling quantum foam, where the very notions of before and after, cause and effect, may dissolve. We need a theory of quantum gravity to describe this regime, and we do not yet have one. String theory, loop quantum gravity, and other approaches offer tantalizing hints, but no consensus, no confirmed predictions. So the singularity is not the beginning. It is the point where our current understanding fails. Beyond it, or rather at scales smaller than the Planck length and times shorter than the Planck time, the universe enters a realm we can speculate about but cannot yet definitively describe. This is where the story becomes thrillingly open. If the Big Bang singularity is not the origin, what is? One leading idea is cosmic inflation, proposed in the early 1980s. Inflation posits that a tiny fraction of a second after whatever initiated the universe, space underwent a period of exponential expansion. In an almost inconceivably short time, a region smaller than an atom ballooned to a size larger than the observable universe today. This rapid stretching solved several major puzzles. It explained why the universe is so uniform. Distant regions that seemed too far apart to have ever influenced each other were once close enough to equilibrate before inflation blew them apart. It explained why the universe is geometrically flat. Inflation stretched any initial curvature to near invisibility, like inflating a balloon until its surface looks flat. And it provided a mechanism for the tiny density fluctuations we see in the cosmic microwave background. Quantum fluctuations in the inflating field were stretched to cosmic scales, becoming the seeds from which galaxies eventually grew. Inflation is remarkably successful at explaining the observed features of our universe. But it pushes the question of origin back one step. What caused inflation? What was the state of the universe before inflation began? And crucially, inflation typically requires very specific initial conditions itself. It does not arise from just any starting state. So we have not found the beginning. We have found a successful description of a very early epoch, but the ultimate origin remains elusive. Another radical idea comes from quantum cosmology. In quantum mechanics, particles do not have definite positions or trajectories until measured. They exist in superpositions of states. Apply this thinking to the universe itself. Perhaps the universe does not have a single definite history, but exists in a superposition of all possible histories. Stephen Hawking and James Hartle proposed the no-boundary proposal. In this framework, time itself is treated as a quantum variable. Near the Big Bang, time might not be a clear-cut parameter. It could behave more like a spatial dimension. Asking what happened before the Big Bang is then like asking what is north of the North Pole. The question is malformed because before assumes a classical notion of time that does not apply. The universe is finite in the past but has no boundary, no edge, no initial moment in the conventional sense. It simply is, emerging from a quantum state where distinctions like before and after do not exist. This is mind-bending. It suggests that the universe is origin, is not an event in time, but a feature of the quantum geometry of space-time itself. Feynman would have appreciated the honesty required here. He famously said that nobody understands quantum mechanics. Not in the intuitive sense we understand everyday physics. Quantum mechanics works. Its predictions are astonishingly accurate. But the meaning, the why, remains elusive. Applying quantum mechanics to the entire universe magnifies this interpretive challenge. We cannot stand outside the universe to measure it. We are inside the system, part of the quantum state. The usual notion of an observer collapsing a wave function does not apply. Who or what observes the universe? These are not just technical problems, they are deep conceptual puzzles about the nature of reality, existence, and knowledge itself. The origin of the universe sits at the intersection of physics and philosophy, and our current tools can take us only so far. There is also the multiverse hypothesis. If inflation happened once, it likely happened many times, and may still be happening in regions of space beyond our observable horizon. In eternal inflation, the process never fully stops. It ends in some regions, giving rise to bubble universes like ours, but continues in others. Each bubble could have different physical constants, different laws, shaped by how the underlying quantum field settled. Our universe, with its particular values of fundamental constants, is just one bubble in an endlessly inflating cosmic foam. In this picture, the Big Bang is not the beginning of everything, only the beginning of our local patch. The larger multiverse may be eternal, with no beginning or end. This is speculative, but it arises naturally from inflationary theory. It also reframes the question of fine-tuning. Why is our universe so precisely calibrated for life? Perhaps because there are countless universes with different properties, and we inevitably find ourselves in one where conditions permit observers. This is the anthropic principle applied on a cosmic scale. It does not explain why the multiverse exists, but it shifts the mystery from why our universe is special to why there is anything at all. Feynman was skeptical of untestable ideas. He valued theories that made predictions you could check. Much of what we are discussing, singularities, quantum foam, the multiverse, lies at or beyond the edge of testability with current technology. But that does not make them unscientific. They are extrapolations from well-tested theories, attempts to follow the logic of relativity and quantum mechanics into regimes we cannot yet directly probe. The key is that they are not arbitrary. They are constrained by the mathematics and by consistency with known physics. Future observations, perhaps of gravitational waves from the early universe, or more detailed maps of the cosmic microwave background, might offer indirect tests. The James Webb Space Telescope and next-generation experiments are pushing the observational frontier. But some questions may remain forever beyond our empirical reach, knowable only through theoretical reasoning and consistency arguments. What does all this mean for the Big Bang? It means the Big Bang, as commonly understood, is a misnomer. It was not an explosion. It was not the creation of space and time from nothing. It was a transition from an earlier state we do not yet fully understand to the hot, dense, expanding state we can describe. The universe's observable history begins at the end of the Planck epoch, roughly 10 to the minus 43 seconds after the putative singularity. Everything before that is conjecture, informed conjecture, but conjecture nonetheless. The Big Bang marks the start of the classical expanding universe, but the origin, the true beginning, if there is one, remains hidden behind a veil of quantum gravity. Feynman would insist we be honest about this. Science is not about certainty. It is about the best provisional understanding we can achieve with the evidence and tools we have. And right now, our best understanding is that the Big Bang was not the beginning. It was a chapter. Perhaps the first chapter we can read, but not the opening line of the story. This humility does not diminish the achievement. The fact that we can trace the universe's history back to fractions of a second after its emergence, that we can predict and observe the cosmic microwave background, the formation of elements, the growth of galaxies, is extraordinary. We have decoded the universe's adolescence and adulthood with remarkable precision. But childhood, infancy, and conception remain mysteries. And that is where the frontier lies. That is where the next generation of physicists will venture, armed with better mathematics, more powerful telescopes, and deeper insights into quantum gravity. The question of why there is something rather than nothing, why the universe exists at all, may never be fully answered. But the quest to understand how it began, or if it began, is one of the most profound endeavors humanity has ever undertaken. And the shocking truth that the Big Bang was not the beginning is not a defeat. It is an invitation to look deeper, to question further, and to marvel at the astonishing, mysterious, and gloriously incomplete picture of reality we have